Quantum physics is arguably the best explanation of reality that we have. It is also notoriously mind-boggling, fascinating, and counterintuitive. The A-level course barely scratches the surface of how weird the world of quantum is, but I hope to give a glimpse of just how different the universe is to how we expect it to be. In this video, we will analyse two types of universes. One where things are continuous, which I will call the classical world, and one where things are discrete, which I will call the quantum world. The best way to describe what this means is to look at a simplified model of an electron in an atom. We know that from electric fields that the electron will have a specific energy depending on how far away it is from the nucleus. In a classical world, we could just gradually, smoothly move this electron further and further away from the nucleus, and it would gradually increase its energy. However, in a quantum world, this electron can't move smoothly, but can only jump between specific distances, each with associated energies. It is simply not allowed to exist at any of these intermediate distances. In both worlds, the electron can exist at these two places. However, to get from one point to the other, in the classical world, it goes via an infinite number of close together positions in between, whereas in the quantum world, all it can do is jump straight there. Now let's look at the phenomena of light and how classical and quantum worlds disagree. In the classical world, light comes in waves spread out over space, which have wave properties like wavelength and frequency, and the energy of the wave is the amplitude squared. When this light hits an object, whatever energy is in the wave can be passed gradually as the object soaks up more of the wave. If the light wave has a greater amplitude, the wave will transfer more energy, but it will still be soaked up gradually. In the quantum world, light exists as small packets of energy, which are particles, called photons. We take the frequency of the light wave in the classical world and state that the energy carried by each photon is equal to this number, called Planck's constant, multiplied by the frequency. When a photon hits something, either all or none of this energy is transferred, and never any amount in between. The difference between these two worlds becomes clear when we study a phenomena called the photoelectric effect. To understand the photoelectric effect, we can again look at a very simplified version of reality. Imagine that a sheet of metal is made up of an array of atoms next to each other. All of these atoms have electrons, and most of these electrons just orbit around the nucleus of each atom, as you would expect. If an electron is orbiting its nucleus like this, we will say that it has zero energy. In a metal, if an electron gets a certain amount of energy, which we call phi, it is allowed to leave its nucleus and join a sea of delocalized electrons that move around the metal freely. We can easily measure how many electrons are in this sea, for example by connecting a circuit and seeing what current flows. We are going to examine two different cases here and see how they differ in the classical and quantum worlds. Firstly, we are going to imagine shining light with a low frequency onto this metal. This means that in the quantum world, each photon has a low energy, which is less than phi. In the classical world, as the light continues to bathe the metal over time, a bound electron which starts at zero energy gradually soaks up more and more energy, gradually increasing until it reaches phi, and then it joins the sea of delocalized electrons. In the quantum world, when a photon hits the metal, the electron simply cannot absorb any of this energy. Whilst the electron can exist at zero energy around the nucleus and at phi energy in the sea of electrons, it can't exist with any intermediate energy. And since the photon can only give away all of its energy at once, or none of it, it has to give none of it. Therefore, we will not find any delocalized electrons. If we use light with high frequency, and so a high energy of photon in the quantum world, the classical world will undergo much the same experience as before, soaking up the energy until the electrons become delocalized. In the quantum world, the energy the photon has to offer is now sufficient to jump over the no-go zone and into the delocalized sea for us to detect. We can see now that these two worlds give noticeably different outcomes. All our experience in everyday life suggests to us that we live in a continuous, classical world. Usain Bolt ran the whole 100 meters. He didn't just jump instantaneously from the beginning to the end. However, thousands of extremely precise experiments taken all over the world over the past 100 years tells us that we in fact live in a discrete quantum universe.